Hello and welcome to this second session on two-port network. So in the last lecture we discussed about a two-port network and jet parameter. Okay, so a two-port network is basically a network that has two port. Okay, and what we mean by port is basically a collection of two terminals. So one terminal is used for current to enter into the network, and second terminal is used for current to exit. So you can see that from this port 1. So this part here is our port 1. Okay, and in this port 1 the current I1 is entering through this first terminal and leaving through this second terminal. So overall total current that is coming in or out of this network from port 1 is equal to 0. Similarly, you can see that here we have port 2, and along this port 2 we have the voltage across this is V2, and current is entering from the positive terminal and leaving through negative terminal. So this is going to be the convention. So given a two-port network, we have access to this terminal voltage and current. So we have this port voltage and current here that is available to us, and we would like to know how these are related with each other. So in that regard, we consider two of them as independent variable and two of them as dependent variable. Now when the current at input port as well as output port is independent variable, in that case the relationship that exists is given in terms of Z parameter, and we have discussed about this in length in the very last lecture. So V is equal to Z times I, where V is a voltage vector of V1 and V2. It is also the dependent vector, and then we have another vector I, which is consist of I1 and I2. This is going to be independent vector, and this vector V is dependent upon I, and this relationship is described by this Z parameter or Z matrix. Okay, so the number of Z parameters that we have is Z11, Z12, Z21 and Z22. Okay, now Z11 will be calculated by taking the ratio of voltage at input port, that is V1, and I1, current at input port, and this is under the situation that I2 is equal to 0. So in this equation you can clearly see here that when I make I2 equal to 0, this I2 equal to 0, in that case what is going to happen? V1 will be equal to I1 Z11, okay, and V2 will be equal to I1 Z21. So Z11 can be calculated as V1 by I1, but the underlying condition here that is kind of described by this vertical line, and then I have written here I2 equal to 0. It means that there is no current at output port, and which essentially means that output port is open. So that's why Z parameter is also known as open circuit parameter. Similarly, we can calculate Z21 by taking the ratio of V2 and I1, and at that time again I2 is equal to 0, so output port is again open. So when output port is open, we can calculate Z11 and Z21. Similarly, when input port is open, then by taking the ratio of V1 and I2, we can calculate Z12, and V2 and I2 we can calculate Z22. Okay, so this is exactly what we are going to do here. Okay, so this should be 1, not 2. Okay, so this is so we are now what we are going to do is that we will be solving a problem based on this Z parameter. Okay, so let me give you a network here, and that we will try to find out these Z11, Z12, Z21 and Z22 given a network. So let's consider a T network, also known as star network. So here we have one resistor, and then we have another resistor here. Okay, and yet another resistor is vertically here. Okay, this is connected like this. Now let's assume this to be our output port and this as our input port. So left side is input port, right side is output port, and we have to find out what is going to be Z11, Z12, Z21 and Z22. Okay, so let me give the value. This is 40, let's say this is 60, and let's say this is 30. Okay, so what is going to be the value of Z11, Z12, Z21 and Z22? So how can we do this? Okay, so this is the very first example that we are going to do, and we will be solving it by that from the definitions only, by making I2 equal to 0 and I1 equal to 0. So this is going to be our method 1. So let's see how we will proceed in method 1. So what we do in method 1 is that let's make first output port as open, and we will apply a voltage source here at input port. Okay, so let me just copy this figure and then we will proceed from here. What I'm going to do here is that I will make second port open. Okay, so here the case 1 output port is open. Okay, so this is anyway open circuit parameter, so output port has to be open for calculation of Z11 and Z21. Okay, now what I'm going to do is that we will apply a voltage source of V1 here. So I will apply a voltage source of value V1 here, and I will apply a current. So I will assume that the current that is coming from this is I1. Now V1 by I1 is going to be equal to our Z11, and you can see that here I2 will be equal to 0. Okay, and the voltage across this is anyway equal to V2. So what we have to calculate here in this circuit, V1 by I1 and V2 by I1. Okay, so for that let me just write down the equation here. So in this circuit you can clearly see that V1 will be equal to 70 times I1 plus 30 so the V1 is going to be 70 times I1 only. We don't have any I2 current, so all the current that I1 is coming here, that is also coming here, isn't it? And similarly V2 can be calculated as V2 will be equal to I1 times 30. Now you can clearly see that V1 by I1 here. Okay, and we have already considered I2 be equal to 0, so I can write it that I2 here is equal to 0. This value turns out to be 70, and similarly V2 divided by I1, and again I2 here is equal to 0, so this value also turns out to be 30 ohm. So this is 70 ohm and this is 30 ohm, isn't it? So this value is basically our Z11, and this value is basically equal to Z21. Okay, so this is also known as open circuit input impedance, and this is the transfer impedance that we have calculated. Okay, now let's consider the second case. So this is the first case when output port is open circuited. Now what we are going to do, we are going to make input port open circuited, and then we will calculate the ratio of V1 by I2 and V2 by I2. Okay, so let's just see that. Now in this circuit what I am going to do, I will be applying here so in this circuit I am going to apply a voltage source here that will be equal to V2. Okay, and I'm going to assume that current coming out from this to the circuit is equal to I2. So this is V2, and I1 is that we haven't applied anything here, so I1 will be equal to 0. It is open circuited, but there is going to be a voltage here, and that voltage is V1. So now in this circuit we have to calculate V2 by I1, V2 by I2 and V1 by I1. So you can clearly see that V2 will be equal to 90 times I2, and V1 is going to be equal to 30 times I1. Okay, from here you can clearly see that V2 divided by I2, and given I1 is equal to 0, turns out to be 90. And from this relationship you can see that V1 divided by I2, given that I1 is equal to 0, turns out to be 30. Okay, so this value here is our Z22, and this value here is Z11. 1, 2. Okay. So the value that we have calculated here is, so this Z matrix is going to be, so the Z11 value was 70, isn't it? Z12 value turns out to be 30. Z21 value also turned out to be 30. And Z22 value turns out to be 90. Okay, so this is going to be Z matrix and these are going to be our parameters. So this is one way of calculating this Z parameter. Okay, now one thing that you will notice here, that this value that is Z12 and Z21 is equal. So given a purely resistive network, this is always going to be true. Okay, and why it is going to be true, we are going to explore that in the future. But for now, you can notice that given a purely resistive network, you are always going to have Z12 equal to Z22. So let's move on to the next method of solving the same problem, and then we are going to wrap up this session. Okay, so in the second method, so this is going to be our method number 2, and the second method what we are going to do is that we will apply V1 and V2 simultaneously. Anyway, what we want to do is that we want to get relationship of like this, that V1 should be given in terms of I1 and I2 variable only, and V2 should be given in terms of I1 and I2 variable only, isn't it? So if we eliminate all the other variables from this network, then that whatever, so we basically what we are going to do is that we will try to represent our relationship like this equations here, right? So we will write V1 in terms of I1 and I2, and we will write V2 in terms of I1 and I2, and we will eliminate all other variables that is there. Okay, so if we can write it like this, then we basically, if we compare them, that relation with these equation, we will get the value of Z11, Z12, Z21 and Z22. Okay, and oftentimes it's much easier than considering the same circuit twice. Okay, as you can see that in the previous method we have done that. So this is method number 2, and for this method what I am going to do is that I will apply a V1 here. Okay, so our voltage V1 will going to be applied at port 1, and we will assume that the current I1 is coming out of this, and then after that we will apply a voltage V2 here, and we will assume that current I2 is coming out of this. Okay, so if we write this in this first mesh like this loop, so in this L1 loop, if we apply this KVL in L1, so applying KVL in L1 mesh, what we are going to get, so we will have V1 equal to 70 times I1 plus 30 times I2. Similarly, if we do the same thing in outer loop, so this is V2. Okay, so we will have V2 equal to we will have V2 equal to 30 times I1. Okay, plus 60 plus 30, 90 times I2. So if you compare this with above mentioned equations, you will see that V1 and V2 is here as one vector, isn't it? And then you have this Z matrix here, which is 70, 30, 30 and 90, and then you have here your current vector, that is I1 and I2. Okay, so from this you can clearly see that your Z matrix, Z parameters are this 70, 30, 30 and 90. Okay, so this is yet another method of finding out the two-port network parameter. So in certain times one method may yield a fast and better result. I mean, not better, eventually you are going to get the same answers, but one method may be preferred in certain situation over other, depending upon what kind of circuit you have. Okay, so we are going to end this session here, and I will see you in the next session. Thanks for joining in. Thank you.